Hello, this is Dr. Lori. Welcome to this next discussion about converting numbers to graphs and back again. So if you remember, when we have any kind of a continuous variable, or also called scale, the best descriptive statistics for that are for the picture would be a histogram, and for the descriptive statistics would be a mean and a standard deviation. Well, if you were given a mean and a standard deviation, would you be able to convert those into a histogram? And that's what this is all about, this video lecture. So what I'd like to show you is an example that gives you a mean of 100 and a standard deviation of 15. And you'll see in a minute why I selected this one. So if we're drawing a histogram, we make a somewhat reasonable assumption that this distribution is at least fairly normally distributed. And by normally distributed, what we mean by that is that it's a bell-shaped curve and that it's symmetrical. That's not exactly perfect, but it's close enough. And so somewhere down here along the x-axis is, if I draw something close to the middle, this is the mean. And then if I draw approximately, give or take, this tail is kind of weak. It's too low, but we'll use this anyway. If I split this curve into approximately 4 equal pieces, given that there should actually be a little bit more of a tail, I'll draw it like this so that you can see it. I can't probably erase that other one, but we'll just leave it there. So we're dividing this into about 4 equal pieces. What you end up with is a graph that shows approximately what percent of this particular sample or population, whatever this histogram is of, is in any given range. And the way this works is that the standard deviation measures something akin to the average distance from the mean. So we have here, like, there are actually people in all of these areas of the graph, and this one standard deviation away on either side is conceptually, it's not technically mathematically accurate, but conceptually this is the average distance away. Some of them are more farther away, and some of them are not as far away as this standard deviation. Some of them are really far away, and some of them are pretty close. But on average, they're a certain distance away, and that's called put the number 1 standard deviation away. And some of them are to the left, and so the ones that go here to the left are -1 standard deviation to the left. If we were to mark these two as well, this is 2 standard deviations away. They're intended to be evenly spaced, or -2 standard deviations away. And so if we were to then add this information to the graph, what we end up with is that our mean is at 100. So here we have our scale kind of going along. Here's our 100 point at the mean. And then at 115, we have 1 standard deviation because it's 15 above. This difference is 15. And at 130, we have 2 standard deviations above the mean. And this scale actually continues above and below to go to 85, and similarly 70. So each of these intervals should be 15. Here's another interval of 15 because each standard deviation is 15 wide. Now, another important feature of this histogram is if it is a normal histogram, a certain percentage of that sample will fall in a specific range. And let me give you those. Many of you have learned about this in either your elementary or secondary or college statistics class, so this might be a review for you. But within this area that goes between +1 standard deviation, here's your +1 standard deviation, to -1 standard deviation, the percent under the curve is 68%. These are just simply numbers that you would have to memorize. So this area right here accounts for 68% of my sample. That's a big chunk. That's a little bit over 2/3. And I'm going to use approximately, give or take 2 standard deviations, plus or minus, above or below this area right here is 95%. So going all the way from here, all the way up to here, that area is 95%. And that's going to be an important number when we start talking about probability and inference, because we want less than a 1 in 20 chance, in other words 5%, that we got the wrong answer. So this 95% gives us 19 out of 20 chances that we are in the ballpark that we were expecting. So 95% of our sample is falling within this particular range. What that means is that there's 5% left. And that's partly why I redrew the tail over here, because it had to show something. Here, and let's draw it with a nice bright yellow color. In this area right in here, kind of going out the tail, and in this area right here, going out that tail, those two need to add up to the other 5% that's not in this 95% area. And so what that means is that in this tail, let's undo that, in this tail right here, 2.5% is in there, and in this tail right here, 2.5% is in that tail. These are kind of features that go along with what we've learned about the histogram and the mean and the standard deviation, is we're now applying those concepts to the actual graph. So let's do another example, and this time instead of using 115, let's change those numbers. Let's have it be a mean is equal to 40 and a standard deviation is equal to, let's say, 5. So in this case, we have the same exact normal curve. That doesn't change. What's changing is the actual scale that goes along the bottom here. So instead of being centered at 100, we're going to have our mean at 40, and this 1 standard deviation above and 2 standard deviations above, that interval is 5. So 40 plus 5 is 45. 45 plus 5 is 50. And then 1 and 2 standard deviations below the mean is 35 and 30, respectively. So what this tells us is if we're given some specific numbers, we can actually convert it to the scale that goes along with the graph that we would use to draw that particular item. Now, this can go somewhat wrong so what could possibly go wrong? What can possibly go wrong is if you have significant, again I want to stress the word significant, either skew or kurtosis. And so what I want to do is really take a look now at what that skew and that kurtosis looks like. One of the things that students sometimes struggle with is keeping track of left skew and right skew. So what I want to do is I want to draw them for you. Left and right. And I'll draw the curve, but then I'll put an extra long tail over where the skew is. And so what I want you to imagine is if this was a normal curve and it was even, it was a mirror image to the left and the right, and you took hold of this left side and you pulled it to the left, that would cause this curve to be pulled over to the left. It's also called negative skew. And then similarly, we could draw right skew where we have ended up with a long tail off to the right. In other words, I grabbed onto this tail over here and I pulled it over to the right. Right is also called positive skew. And the reason that's a problem is because now my mean is no longer in the middle of the main part of the lump. In other words, when I have significant right or left skew, then the highest point might be here, but my mean will get pulled in the direction of the skew. It's as if the mean, this is the median, the mean, it's as if it's tethered to the direction of the pull or to the direction of the skew. And so that can be problematic because what we've said is our middle is in a specific place. Well, when we have skew, our middle really isn't necessarily, that's not a good depiction of where the middle is. In other words, drawing a histogram would be deceptive when we have significant right or left skew. The other thing that can happen is if you even have a single outlier. So let me draw that on here. In a data set that's extreme, especially if it's an extreme outlier. And I want to give you an example. Typically, cholesterol values are somewhere in the 100s, sometimes up to 200s. And so this is kind of the normal range that you would see. But every once in a while, you'll come across a value that comes out of the lab that's in the 1,000 or 2,000 points. Now, if you looked at that in your data set and you looked at that extreme value, you'd say, I wonder if the lab accidentally added an extra 0 and it really is supposed to be just 200. But what if I told you there are some individuals that have a specific kind of disease that actually causes their cholesterol, hypercholesterolemia, to be extremely high? And so that's a real value. When you look at their blood sample, you can actually sometimes see the cholesterol crystals settling out in the blood. The cholesterol is so high. And so these people have significant problems. Now, what if you only had a sample of, say, 10 people, and one person is way over here, and the other 9 are in this sort of normalish range? What happens is it pulls your average, which should be somewhere in the hundreds and 200s, quite a ways out. because this is such a big number that this outlier or extreme value can really have a profound influence on the mean. So when you have these situations where you have skew or kurtosis where it's either super pointy or super flat, these values, the mean and standard deviation, does not do justice to accurately describe the actual shape of the of that particular sample. And so we just need to be really careful when we're saying the mean is this and the standard deviation is this, that we also take a look to see if we have skew or kurtosis or some extreme outlier type situation, because then the numbers aren't really reflecting they don't give an accurate picture. So having said that, then we'll move on to talking about box plots. So join me in my next video.